You know, inside your head right now, there's one of the most incredible symphonies in the entire universe happening, the electrical activity of your brain. Today, we're going to plug in. We're going to break down the amazing technology that actually lets us listen in on this constant, complex conversation between your neurons.
Seriously, think about it. Right this second, your brain is firing off millions upon millions of tiny electrical signals. It is a non-stop storm of activity. But how do we get from that crazy storm inside your skull to a meaningful signal we can see on a computer screen? Well, that is the big question we're going to tackle today.
To answer that, we have to start small, and I mean really small. We're going to go on a journey from the fundamental electrical charge of a single neuron all the way up to the course of millions of them working together. So let's find the source of that buzz.
Okay, so everything, and I mean everything, starts right here, with something called the electric membrane potential. The easiest way to think about it is that every single one of your neurons is like a tiny biological battery. You see, there's a different mix of charged ions inside the cell compared to outside, and that difference creates a little bit of electrical voltage. This is it. This is the foundational power source for every single thought you have.
Now, you've probably heard of the action potential, right? It's that famous all-or-nothing electrical spike that neurons use to send signals down the line. But here's what's so interesting. Those big, loud spikes aren't actually what EEG and MEG are listening for. Instead, they're tuning in to something way more subtle, graded potentials. Unlike that big all-or-nothing spike, these signals are proportional to whatever is stimulating them. And, this is the crucial part, they can add up.
So the bottom line is this. The signal we can actually detect from outside your head comes from these little graded potentials happening at the synapse. That's the connection point between neurons. They're called postsynaptic potentials. When one neuron sends a message to the next, ions flow, and these small, summative changes are the tiny whispers that, when they all combine, create a chorus we can actually hear.
Okay, so we found the whisper, but how does that tiny electrical change from just one neuron become a signal that's strong enough for us to measure from way out here? Well, this is where teamwork comes in. Let's see how that whisper builds into a roar.
So, meet the stars of our show, the pyramidal neurons. These guys are the most common type of neuron in your cortex, especially in layers 3 to 5. And what's so special about them is their shape. They're long and all lined up, which makes them absolutely perfect for creating a combined, measurable signal. You can think of them as the main singers in our brain's choir.
For their individual signals to actually be heard, three things need to happen. First, you need thousands of these pyramidal neurons to be physically aligned, kind of like singers standing in rows in a choir. Second, they have to be oriented in parallel, all facing the same direction, perpendicular to the surface of the cortex. And third, and this is a big one, they have to activate synchronously. They all have to fire at roughly the same time.
And this brings us to a really cool concept called the equivalent current dipole. When all those conditions are met, when the neurons are aligned, parallel, and firing together, the tiny little electrical fields from thousands of them all add up. Imagine each neuron is one person humming a single note. Well, the equivalent current dipole is the powerful, unified chord that the entire choir produces. It acts like one single, much stronger source of electricity that we can finally detect. The whispers have become a shout.
So now that we have a detectable signal, how do we actually record it? This brings us to the two main technologies used for listening in on the brain's electrical activity, EEG and MEG.
First up, we've got EEG, or electroencephalography. It works by putting electrodes on the scalp to measure differences in electrical potential. But here's the twist. EEG doesn't measure the current inside the neuron directly. Nope, it measures the secondary currents. That's the return flow of ions in the space outside the neurons. It's kind of like hearing the thunder after you see the lightning. It's the electrical echo of the main event.
MEG, on the other hand, magnetoencephalography, takes a totally different approach. See, any electrical current, including the one flowing inside our neurons, generates a tiny magnetic field. MEG uses these incredibly sensitive detectors to measure those magnetic fields directly. So if EEG is listening for the thunder, MEG is looking for the lightning itself, the primary current flowing right inside the neuron.
And the scale we're talking about here is just staggering. To generate a magnetic field that's strong enough for even the most sensitive MEG machine to pick up, you need somewhere between 10,000 and 50,000 of those pyramidal neurons all firing in sync. It's a real testament to both the brain's complexity and just how incredible our technology has become.
So let's put them side by side for a second. EEG signals are actually easier to detect, and the equipment is way more flexible and portable.
The downside is that the electrical signal gets smeared and distorted as it passes through your skull and scalp. MEG signals are much, much fainter. But because magnetic fields aren't really bothered by the skull, MEG can give you much better spatial resolution, a clear picture of exactly where in the brain the signal is coming from.
Okay, so we can listen to the brain's chorus, but what is it actually saying? Let's zoom back out and explore what these signals, these brainwaves, can really tell us about what's going on inside our minds.
You know, the signals we record aren't just random noise. They have these distinct rhythms, or waves, that are tied to different mental states. Think about it, that focused, buzzing energy you feel when you're deep in a project. That's likely a spike in what we call beta waves. Or what about that calm, almost floaty feeling you get during medication or right as you're about to fall asleep? That's your brain producing more alpha and theta waves. By analyzing these frequencies, we get a direct window into your cognitive state at any given moment.
Let's look at a specific, totally fascinating example, the P300 wave. This isn't a continuous rhythm like the others. It's a distinct brainwave pattern that appears about 300 milliseconds after you see something meaningful or surprising. It's not about the thing itself, but about your brain's reaction to it. It's like a neural signature of your brain going, "Whoa, that's important," and making a decision about it.
And the P300 is so consistent, so reproducible, that it's become a vital tool for scientists. Researchers and clinicians can use its timing and its strength as a direct measurement of cognitive function. It gives us a powerful, objective way to study how our brains process information and make choices.
And the applications go even further, into the clinical world. This slide here shows data from a study that compared brainwave patterns in people with autism spectrum disorder to a control group. You can see right on the chart how it visualizes the differences in the intensity of various brainwaves, revealing really distinct neural patterns between the two groups.
So what does this all mean? Well, these differences in brainwaves suggest there might be variations in how different regions of the brain communicate and integrate information. And this kind of analysis is absolutely crucial because it can lead to objective biomarkers that help us understand the unique sensory and perceptual experiences associated with conditions like ASD.
So, we've journeyed all the way from the tiny electrical potential of a single neuron to decoding the incredibly complex language of brainwaves. We've developed these amazing tools to listen in on the brain's symphony, and this leaves us with a final, pretty profound question. As our understanding grows, what happens when we move beyond just listening and we learn how to help write the music itself?